Okay, time to prove time to prove constant rank level set theorem, which is just a corollary from last two statements we've proved. Basically, the existence of the well, you know, consequence of constant rank in a neighborhood is to find find change of coordinates on the domain and codomain such that the smooth map F takes elements in the through the change of coordinates or charts in manifold language. It just while going from Rn to Rm, it forgets the last n minus k coordinates if your rank of f star is k, constant in a neighborhood U. Now we've proved that for a manifold case and also the Euclidean case. Now coming to the regular submanifolds again, if f m to n is a smooth map, and C is in n, suppose C is in n, for which there exists an open set U in M containing F inverse C, such that the rank of the F star map from TPM to TF of Pn is constant and K for all P in U. Then F inverse C is actually a regular submanifold of M of codimension K. We'll remark something important after proving this. The fact that rank of the F star may actually increase in a neighborhood but cannot decrease. This will be related to submersions and all that. We'll do that after writing this corollary, okay, proving this corollary. So consider for P the for P the F inverse C inverse C for P in F inverse C by constant rank theorem, there are charts U, phi containing P and V, phi containing F of P, such that psi composed with F composed with phi inverse of X forgets the last n minus k coordinates right. So then we are taking centered at C, okay. that. Okay, then f so f inverse of c equals to c is phi inverse of 0, right? Psi is a diffeomorphism, so it is precisely f inverse of psi inverse of 0, right? And okay, let's write it as phi we want to show that u gives the adapted chart, so let's just say u intersection f inverse of c. Let's see what this is. So this is precisely psi sir. This is precisely the inverse of psi composed with f composed with phi inverse, right? Inverse where at 0. So it is again precisely the set x in phi of u such that phi, okay, psi composed f composed phi inverse of inverse at 0, okay, and this is basically all the points in f phi of u such that the starting x1s are 0, because this maps to exactly 0, so it has to be 0. Yeah, so precisely the first game. And x1 equals to xn equals to 0. Yeah, so u comma phi is an adapted chart of f inverse of c. Neat. Yeah. Yep, that's neat. Now let's come to a very important concept of immersions and submersions. Immersions and submersions. Note that, okay, let's just note that the rank of f star, where f m to n is a smooth map between smooth map can increase in a neighborhood but won't decrease because the A is the submatrix is a submatrix of oh my god matrix of where A is a submatrix of a star definition. Let f m to n be a smooth map. F is called an immersion at P in M if f star TPM to T f of P n is injective. Called an immersion if it is an immersion. And similarly, F is called submersion at P in M if f star TP M to TF P n is surjective, and F is called submersion if it is a submersion at all points of M. Corollary. This is a very interesting corollary. Very interesting corollary is that F M dad. Okay, let's just be a pro and define this. Define a snippet for the smooth map. Okay. So what do I need here is a snippet for FMN. Why do I want FF? This is FF, right? FM to N to I will just copy this to include a dimension M to N fair enough. Yep. So FF that is so pulled up. Why did I not think of that, man? Just a space. Just give a fucking space. Cool. Okay. F into N is in fact FFD. We need FFD is a smooth map. If F is an immersion at P, then there are charts U, 5 centered at P and V comma psi centered at F of P such that standard F of U is subset of V and psi circ F circ phi inverse of x1 xm equals to x1 xm 0. So the first thing is that if F is an immersion at P, then there are charges U, phi centered at P and V, phi centered at F of P such that F of U is a subset of V. So, and psi O F O phi inverse of x1 so on up to xm is precisely x1 xm 0 0. Okay, so this is simple to see because F star is an injection. The moment if it's an injection, then the rank of F star is maximal. It is either m and or n, which are the smallest. Right now, it's maximal and also the rank is fixed. If it's an injection, then m has to be greater than n, m greater than or equal to m, so it's the rank n. Right, so yep, if it is immersion at point, then it's actually immersion at a neighborhood because the rank doesn't decrease, it can only increase, and the maximal rank is fixed because it's an injection again. So yeah, so it is immersion in a neighborhood, and in a neighborhood you have a constant rank, which is basically the full rank of F star, which is either m or n, but it's injective, so it's n. Sorry, it's m. It's m actually. Yep. It's m. Then by the constant rank theorem, this is just really true. What if it's a submersion at P? Okay. We'll have a remark to say. This looks like an inclusion map, right? Immersion is a prototype of an inclusion. We'll remark that soon. What we want, the second part of the corollary is about submersions. If F is a submersion at P in M, then there are charts U, phi centered at P and V, psi centered at F of P such that F of U lies in V and this is the statement that the submersion is a prototype of projection map. Psi circ F circ phi inverse of x1 xm equals to, now recall that M is an n-dimensional manifold, and if it's a submersion, so it is a surjective map. So M is greater than n, so the rank of F star is n, constant in the neighborhood. So rank is n. So you will have charts such that yeah, you will have charts such that wait. Okay, I need to correct that. The rank is n, which is less than m. It's an immersion, so it's an immersion, so m is less than or equal to n actually, right? Here m is greater than or equal to n. Yeah, it's interesting that m is less than or equal to n, and then for submersion, what you have is that it sort of projects. Sorry, this is a projection. So m is greater than or equal to n in this case because it's a surjection. The rank is mn here, and the rank before was n. My mistake. And yep. It projects onto the first n. Note that phi is indeed an n manifold. So from phi you just take the projection map onto it, right? Yeah, it's not necessarily homomorphism charts and all that, but yeah. See, it's a constant rank in a neighborhood, so centered at f of p such that Okay, let's think about how, for all numbers we had from last lecture, we had that constant rank theorem that you can project out, you can precisely, if the rank is k, then you can just project out k coordinates in n. So that is precisely what is happening here for the immersion case. Basically the maximal rank is m, the rank is m, yeah, this is not greater than rm clearly, so rm wala m. So this just first, the immersion is straight from the constant rank theorem, nothing to do. By constant rank theorem, immersion is immediately a proto is immediately immersion. The result follows immediately for the immersion at P. For the immersion at P. But when you take a submersion, the rank is now n, m is greater than n. So what happens is, again here you just project out. So m is greater than or equal to n here, and you yeah, you basically, out of m coordinates, you take the first n coordinates and project it there. That's the statement. What the statement of constant rank theorem says is that you have zeros the next to xn, right? Now, well, x1 xn 0 0 0, this is basically isomorphic to x1 xn, right? I mean, you don't have to show anything here. Yeah. Precisely. There will be the number of zeros that will be in the constant rank theorem also. The number of zeros that will be are precisely n minus k, n minus n here 0. There will be no zeros basically. Wow, that is nice. This is straight output of constant rank theorem. The results follow immediately. For k equals to n, remarks, mark perhaps, the immersion is basically a prototype, of an inclusion map. And while a submersion is a prototype of a projection map. Yeah. This is nice. This is really nice. So this is so natural result. Like, why do you define such an immersion and submersion? This is the reason, right? You have a constant rank theorem that says that you can do this for immersion. That the state, in fact, the constant rank theorem itself says as a special case for k equals to m and n. It just tells you ki it's a inclusion and a projection map. We are just trying to formalize the fact that k is maximal, and either one of them. There are two cases. It could either be a that f star is an injection or f star is a surjection, or both perhaps. Then it's just a diffeomorphism, right? It's at least a local diffeomorphism. Yeah. Then you know, yeah, you have these two cases. Corresponding to that, you have two results for two special cases of constant rank theorem, which just gives you the immersion submersion theorem. So there is another very, again, enlightening definition that a smooth map m to n is called an embedding if, wow, I felt so powerful when I just snipped fm to n out. So a smooth map fm to n is called an embedding if f is an immersion, and also f, okay, f from m to f of m is a homeomorphism where fm has the subspace topology of m. If the domain M is compact, then continuity and bijection implies homomorphism, closed map. Closed set in a compact set is compact, so it goes to a compact subset of f of m of n, then is Hausdorff. So a compact subset of a Hausdorff space is closed. let's see some examples or non-examples. So yeah, let's talk about the definition of embedding, right? A smooth map Fm to n is called an embedding if F is an immersion and Fm to F of m is a homeomorphism where F of m has the subspace topology in n. Okay, it's called an embedding. Okay. So F is an immersion. That means that locally F is just inclusion map. So cool. And Fm to F of m is a homeomorphism. I see. See, it's not trivial, right? F has to be injective. Basically, F has to be injective on this Fm to FFM. Basically, F has to be injective. That's the point, no? Huh? Isn't it? This just follows, no? Because F is a smooth map. What? Okay, well, it has to be a subspace. F of m is a subspace. F of m has subspace topology, so that might be non-trivial. You're saying that. I mean, this is a question of basic topology actually, but we'll see some examples to enlighten us about these requirements of embedding, of these requirements of two facets of two aspects of embedding. So let's consider F. Let's consider F R2, no, R to R2. R2 defined as f of t equals to t square comma t cube. Okay. Then f prime of t equals to 2t comma 3t square and f prime 0 equals to 0. Cool. So what we have is f prime t is 2t comma 3t square, f prime 0 is 0. Okay. Cool. So f star from t0r to t0r square so yeah, f star, the kernel of f star is basically 0. Only 0, right? So it is injective. It's an injection. It is precisely given by the Jacobian, right? So what is the Jacobian? The Jacobian is basically 2t common 3t square, which is 0 if and only if t is 0. So it's an immersion. At 0 it is an immersion. Oh, what? What? The rank is what? Rank is 0. So you're saying the rank is 0, right? So yeah, let's just write that 0. So f star 0 from t0 to t0 r2 is a 0 map. Yep. It's not surjective. It's not injective. It's trivial. It's f star is 0. Trivial linear map? What do you mean by trivial linear map? Trivial linear map. Matrices basic. Trivial rank 0 matrix. Rank 0 matrix. Rank 0 matrix. However, f and R2 f of R is a homeomorphism. Yeah, how do you show this homomorphism? Simply project it here, right? Yeah, I mean t to t square comma t cube, and then x comma y belongs to this. Okay, well, and then x comma y to just clearly t is not 0 here. T cannot, right? X comma y to t. So t square equals to x, t cube equals to y, t equals to y by x. How can this happen? Because what is the inverse on this? Okay, I mean t square comma t cube inverse is again y by x. If you just say x y, just write y comma y by x. It works. Trust me, it works because x square is y cube. Because root x is given that much. Okay. Yep. Trust me, it does. Yeah, it works out. Continuous by for all t is now 0. If t is 0, then just put 0, no? Let put further 0. You cannot go. Let me see. Homomorphism. not an embedding. In fact, f is not a regular submanifold of so again, immersion is locally it's a inclusion. It has to be included in n. That's the intuition sort of thing. So f of m is basically sort of included in n, included in n. Yeah, and we'll continue to the next example. 36. Okay. The next example is consider the set x comma y in R2 such that xy is 0 comma x comma y is greater than or equal to 0. Yeah, this is not a regular submanifold currently. The image of a smooth map this is an image of a smooth map from R2 to R2 but that map cannot be an immersion. Yeah, so we need to find smooth maps sort of that can actually define this. So you have to define piecewise. I suppose that is actually continuous. It's actually smooth. Okay, it's also continuous. So it's like something like phi of t, f of t equals to basically 0 comma e power t, right? And then it goes to infinity e power t, and for what xi equals to 0 you are saying. One has to do one thing, one has piecewise define t greater than infinity. Sorry, what the fuck I'm saying. Let's just say t minus I don't know. Yeah, let's just say 0, like minus infinity to 0, and then comma 0, same thing, right? Equal t comma 0 for t equals to 0 to infinity. What? For t minus 1 maybe. For t minus 1 comma 0, t belongs to 0 comma infinity, and t belongs to minus infinity comma 0. So 0 comma e power t minus 1, such that this is smooth, right? FFT is smooth, and just FT is smooth for both cases, but then you can actually simple thing to be checked to check is just like zero comma 1 by t Hello. Okay. Okay, sorry. So the map cannot be an immersion. Okay, let's just give this map, right? Simple map. I mean, really, how can you just go map continuously from there to there? Um, I think that's all you can do, right? 0, 1 by t. Acha. This is a precise value. Okay, let's for now let's just say this x greater than or equals to 0, comma y. Acha. अच्छा है ना e power t minus 1 by e power. Okay, wait. Let's just say t is equals to minus infinity from 0. E power minus infinity is 0. E power 0 is 1. So you're starting from 0 and then you're going to 1. Same thing here, starting from 1, going to टी को 0 बहुत बड़ा, तो दोनों के लिए ही 0 से ही स्टार्ट होना है, मतलब e पावर माइनस ही रखा ना वो, e पावर माइनस टी, टी टी टेंड्स टू माइनस इन्फिनिटी, it goes to infinity, at t tends to 0, it goes to 0, 0 to infinity हो गया. So then e power t equals to 0, you want it to be 0, yep, that's the map. This is an image of smooth map, but the map cannot be an immersion. For example, consider f of t equals to cases 0 comma e power minus t minus 1 for t less than 1, sorry, for t n minus comma 0. I hope this works. And अच्छा, and e power t minus 1 comma 0 for t in 0 comma infinity. Fair game. This is smooth. And f of r equals to s, but at t equals to 0. Okay, the third example. Third example is a sort of a one cut figure 8, which is G R2 R2 given by G of t equals to t square minus 1 comma t cube minus 1 Wait, what the fuck? I need to plot this on Desmos. That's exactly what I want. I mean, should take humans, right? But that's T. That's exactly what we wanted to do. Then the okay, I won't rush now. I need to go play tennis. Yeah. So yeah, I won't rush things. I will just pause it.